Hello everyone, in this section, we are going to see how biomass can be estimated with data fusion from SAR and optical sensors. The goal is to develop random forest regression model with SAR-optical data fusion in order to predict above-ground biomass. For such a task, there is the need to choose a methodology that is backed by literature to establish the resulted model's credibility in the scientific community. The methodology for this demonstration is partially based on the approach tested by Ghosh and Behera and Ravindran, and to a lesser extent by Lai. Their works used data from SAR, optical backscatter, texture, and vegetation indices to predict above-ground biomass at field plot and global levels with the backbone of regression and random forest algorithms. The considerations for SAR-optical feature data selection is based on studies on SAR for estimating above-ground biomass concluded that C-band backscatter leads to poor performance due to the saturation at biomass values greater than 100 megagram per hectare, as established by Zhang. And also, SAR has been identified to perform poorly than optical data for above biomass estimation where the forest is of high density. While SAR texture gives encouraging results, measurability in local variation in the backscatter and not the values of the backscatter, and this also indicated by Engelhardt and Frank. In addition, SAR L-band penetrating power makes it not suffer from saturation until 300 megagram per hectare, making it a good choice, noted by Urbazev in 2018. These are the justifications for the selections. The above scientific works have guided in giving considerations to layers from Sentinel-1 backscatter and texture, PalSAR-2 backscatter and texture, and that is from the Land Observation Satellite 2, which is called ALOS-2. And Sentinel-2 vegetation indices, and also auxiliary data, which is very important, like land use or land cover map or digital elevation model. The input data set as single images of stacked and co-registered feature bands of the proposed random forest model requirement for training needs to be generated. And platforms like Google Earth Engine can be used to access the various bands identified from the previous discussion for the study area that will be chosen, and also for loading test sites data as an asset to generate a NumPy array for the random forest model. And that is the interface of the Google Earth Engine Explorer on the screen. The synergistic combination of sensory data from multiple sensors will provide a more reliable and accurate estimate as established by the literature. Python can be used to create the random forest regression model to consume the NumPy array from the GEE output. Random forest regressor is a supervised classification algorithm that is formed of decision trees as shown on the diagram. Decision trees are a type of model where decisions are made sequentially, with branching results, usually used for classification or regression tasks. A random forest is simply a collection of such decision trees that are aggregated together into one final result. It functions by building a number of decision trees during training and producing the mean prediction of these trees as an output for regression. Let us look at advantages of random forest. Why are we proposing it? It is one of the most accurate machine learning algorithms. It can handle a large number of input variables, and it has reduced risk of overfitting. performance of the proposed random forest model will depend on a lot of factors, but there are always techniques to make improvements. One is feature space optimization. Multi-temporal and large datasets lead to high-dimensional and complex datasets. Due to a large number of prediction variables or features, especially compared to a small reference data, can lead to high-dimensional problem and leading to overfitting. To avoid this, unnecessary and unimportant features can be discarded from the feature space, thus optimizing it. One next thing is hyperparameter tuning, and that is setting the random forest function parameters to affect its learning performance. One is ablation study, and that is by removing part of the model to judge its impact on the model's performance in order to understand the contribution of each feature to the model. Also, we can look at regional modeling, and that is by building and training the random forest on a given reference site, and then using that to predict other sites within the region. This helps to investigate the ability or the capability of the regional model for predicting other sites in the region. The third one is global model, and that is training with at least one site pair from each site, or a given fraction of the total number of reference sites from all the regions. And this also helps to establish the applicability of the global models for predicting sites in other regions. The accuracy of the model can be assessed by considering root mean square error, relative root mean square error, and also coefficient of determination, of which details are provided. At the end, our model is going to look like the figure we have, where you have the reference data and site selection, then data layer selection. When you come to our dataset, and this is where you have multiple source of data. Sentinel-1, Sentinel-2 and the ALOS PalSAR, the preprocessing stage which will cut across. And from there, you have the input to be generated, of which we want use GEE to generate for the random forest model. We have the feature space optimization we talked about, hyperparameter tuning, data ablation, then you come to the regional models, and at the end you have your predictions. So this workflow can be used to estimate biomass from optical sensing and SAR data. Here is a list of references for further reading. Thank you for your attention.